Steel beams within a residence require bonding when they are incorporated into a lightning protection system. The primary purpose of bonding in this context is to ensure electrical continuity between all metal components of the lightning protection system, providing a low impedance path for lightning current to safely discharge to ground. When lightning strikes a structure, it seeks the path of least resistance to ground. If metal components, such as steel beams, are not properly bonded, the lightning current may find alternative, uncontrolled paths, potentially causing damage to the structure, electrical systems, and even posing a risk to occupants. Bonding achieves equipotentiality, meaning that it minimizes voltage differences between different metal components. This reduces the risk of side flashes, which are sparks that can jump between nearby metal objects if there is a significant voltage difference. These side flashes can ignite fires or damage sensitive electronic equipment. The specific requirements for bonding steel beams as part of a lightning protection system are typically outlined in national and local electrical codes, as well as standards such as NFPA 780, the standard for the installation of lightning protection systems. These codes and standards provide detailed guidelines on the size and type of bonding conductors, the methods for making connections, and the overall design of the lightning protection system. In general, the bonding conductor should be sized appropriately to handle the expected lightning current. This size is usually determined based on the overall design of the lightning protection system and the anticipated severity of lightning strikes in the region. The bonding conductor is typically made of copper or aluminum, and it should be installed in a manner that minimizes inductance, which can impede the flow of high-frequency lightning current. Connections between the bonding conductor and the steel beam should be made using approved methods, such as welding, bolting with specific hardware, or using listed bonding clamps. The connections must be mechanically strong and electrically sound to ensure reliable performance over time. It is important to note that simply connecting the bonding conductor to the steel beam is not always sufficient. In some cases, the steel beam itself may need to be bonded at multiple points to ensure that the entire beam is at the same potential. This is particularly important for long beams or beams that are part of a complex structural system. In addition to bonding the steel beams, other metal components of the structure, such as metal roofing, gutters, downspouts, and metal piping, should also be bonded to the lightning protection system. This creates a comprehensive network of interconnected metal components that provides a safe and effective path for lightning current to ground. The grounding electrode system is a critical part of the lightning protection system. It consists of one or more grounding electrodes that are buried in the earth and connected to the bonding network. The grounding electrodes provide a low resistance connection to the earth, allowing the lightning current to safely dissipate into the ground. The type and number of grounding electrodes required will depend on the soil conditions and the overall design of the lightning protection system. Common types of grounding electrodes include ground rods, ground plates, and concrete encased electrodes. The installation of a lightning protection system, including the bonding of steel beams, should be performed by qualified and experienced professionals who are familiar with the applicable codes and standards. A properly designed and installed lightning protection system can significantly reduce the risk of damage from lightning strikes and protect the structure and its occupants. It is also important to maintain the lightning protection system over time to ensure that it continues to function properly. This includes periodic inspections to check for corrosion, damage, or loose connections. Any necessary repairs or replacements should be made promptly to maintain the effectiveness of the system. Here's a more detailed breakdown of key aspects: firstly, bonding conductor size, secondly, connection methods, thirdly, grounding electrode system, and fourthly, inspection and maintenance. Firstly, bonding conductor size is crucial for safely carrying lightning current. National and local electrical codes, alongside standards like NFPA 780, dictate the minimum size based on factors such as the anticipated lightning strike severity and the overall lightning protection system design. The conductor's ampacity, or current carrying capacity, must be sufficient to handle the immense current surge from a lightning strike without melting or vaporizing. Typically, copper or aluminum conductors are employed. Copper offers excellent conductivity and corrosion resistance, while aluminum provides a lighter weight alternative, though it requires larger sizes for equivalent conductivity. The specific size is determined through calculations that consider the lightning protection system's design, including the number of DIM conductors and the expected peak current. Inductance, the opposition to changes in current flow, is also a factor. A straight, short conductor minimizes inductance, allowing lightning current to flow more freely. Bends and loops in the conductor increase inductance, potentially impeding the current and causing voltage surges. Therefore, the bonding conductor should be installed with as few bends as possible, maintaining a direct path between the steel beam and the grounding system. Secondly, connection methods are vital for ensuring reliable electrical contact between the bonding conductor and the steel beam. Approved methods include welding, bolting with specific hardware, and using listed bonding clamps. Welding provides a permanent, low-resistance connection. However, it requires skilled welders and can potentially damage the steel beam's protective coating. Bolting involves using bolts, nuts, washers, and lock washers specifically designed for electrical bonding. These components are typically made of corrosion-resistant materials and provide a secure mechanical and electrical connection. The surface of the steel beam must be cleaned to remove any rust, paint, or other contaminants before bolting. Listed bonding clamps are specialized devices designed to provide a reliable connection between the conductor and the steel beam. These clamps are tested and listed by independent testing laboratories, ensuring they meet specific performance requirements. The clamp should be compatible with both the conductor and the steel beam materials to prevent corrosion. Regardless of the connection method used, it's crucial to ensure that the connection is mechanically strong and electrically sound. A loose or corroded connection can increase resistance, impeding the flow of lightning current and potentially causing overheating and failure. Thirdly, the grounding electrode system forms the foundation of the lightning protection system, providing a low-resistance path for lightning current to dissipate into the earth. Common types of grounding electrodes include ground rods, ground plates, and concrete-encased electrodes. Ground rods are typically copper-clad steel rods driven vertically into the ground. The depth and number of ground rods required depend on the soil resistivity, which is a measure of the soil's resistance to electrical current flow. Lower soil resistivity requires fewer or shorter ground rods. Ground plates are typically copper plates buried horizontally in the ground. They provide a larger surface area for contact with the soil, making them effective in areas with high soil resistivity. Concrete-encased electrodes, also known as UFA grounds, consist of a bare copper conductor encased in concrete. They are typically installed in the foundation of a building and provide a very low resistance connection to the earth. The grounding electrode system should be installed in accordance with national and local electrical codes. The codes specify the minimum size and number of grounding electrodes required, as well as the methods for installing them. The grounding electrode system should be connected to the bonding network using a grounding electrode conductor. The grounding electrode conductor should be sized appropriately to handle the expected lightning current. Fourthly, inspection and maintenance are essential for ensuring the continued effectiveness of the lightning protection system. Periodic inspections should be conducted to check for corrosion, damage, or loose connections. Inspections should be performed by qualified professionals who are familiar with lightning protection systems. Corrosion can occur due to exposure to moisture, chemicals, or dissimilar metals. Corroded components should be cleaned or replaced as necessary. Damage can occur due to physical impact, such as from falling objects or vehicle collisions. Damaged components should be repaired or replaced as necessary. Loose connections can occur due to vibration, thermal expansion and contraction, or improper installation. Loose connections should be tightened or reconnected as necessary. The lightning protection system should be tested periodically to ensure that it is functioning properly. Testing typically involves measuring the resistance of the grounding system. A high resistance indicates a problem with the grounding system that needs to be addressed. Records of all inspections, maintenance, and testing should be kept for future reference. These records can be used to track the performance of the lightning protection system and identify any potential problems.